I suppose good. Okay, I suppose we can start. This is the first section of FSCD 2021 of today. It is the logical session, and the first speaker is Koji Nakazawa, speaking about the failure of cut-elimination in the cyclic-proof system of bunched logic with inductive propositions. This will be a pre-recorded talk. Now I will switch off audio and video, and after the end of the talk, I will.
This talk
give you
is about the cut-elimination property of cyclic-proof systems, or cyclic
please, Koji.
In particular for the bunched logic. This is a joint work with Kenji Saotome and Daisuke Kimura. At first, what is the cyclic proofs? The cyclic proofs are based on proofs with infinite paths. Here is an example of a proof with infinite paths. This proof proves this conclusion. If this x is either even number or an odd number, then this x is a natural number. This proof admits these two infinite paths that contains some infinite descent. In fact, each infinite path contains infinitely many applications of the unfolding rules. Unfolding rules is here. This E is unfolded to O, and this O is unfolded to E. We call such a condition for infinite paths the global trace condition. It is a kind of soundness condition for the proof system with infinite paths. The cyclic proof proofs are restricted forms of such infinite proofs by the regularity condition. They are finite trees with some circular structure, this one and this one. And in fact, the proof in the previous slide can be seen as a cyclic proof, this cyclic proof. Because these two entailments, this one and this one, these two entailments are the same up to renaming variables. So we can find a cycle like this. The cyclic proofs are considered important for automated proof search for inductive reasoning. Because in cyclic proof systems, we don't have to fix a proposition to prove by induction a priori. So the cyclic proof systems are very important, and we are interested in some fundamental properties of the cyclic proof system. Yes, the cut-elimination is one of the most important property of the proof systems. It means this cut rule does not change the provability. The cut-elimination is important from the point of view of pure logic or the proof theory because it gives some fundamental and important properties of proof systems, such as consistency and subformula properties, and so on. Another merit of the cut-elimination property is for proof search, because the cut rule is problematic to find some proof from bottom to top manner. In general, the cut formula A here is independent of the bottom secant, this one. So if we try to find a proof from bottom to top, we have to find this cut formula A by some heuristic technique. So it is expected that the cyclic proof system enjoy the cut-elimination property. So some existing work have shown that the cut-elimination holds for proof systems with infinite paths for some logic. However, we have proved the cut-elimination does not hold in the cyclic proof system for the symbolic heap separation logic. This result means the regularity condition is not closed under the cut-elimination process. The separation logic is a program logic for pointer programs based on the bunched logic. And the symbolic heap separation logic is a restricted form of the separation logic. Roughly speaking, the symbolic heap separation logic has only the multiplicative conjunctions in linear logic. In the proof, we gave a counterexample for the cut-elimination with binary inductive predicates. That counterexample is provable with cats and not provable without cat. So for these results, we have some natural questions. One is how about the cyclic proof systems for other logics, such as first order logic, linear logic, and bunched logic. The other one is if we restrict inductive predicates, can we recover the cut-elimination or not? So to these questions, we give some answers in this talk. One is the cut-elimination fails in the cyclic proof system for bunched logic either. And the other one is that even if we restrict predicates, inductive predicates to nullary, zeroary predicates, the cut-elimination fails in the cyclic proof system for bunching implication and separation logic. It means the full separation logic, not restricted to symbolic heap separation logic. Okay, and in fact, it seems hard to adapt the proof idea for the symbolic heap separation logic, because BI means bunch logic, and full separation logic contain not only the multiplicative conjunctions, but they have the ordinary conjunction. The ordinary conjunction admits the structure rules, contraction rules, and weakening rules. In fact, these structure rules make the situation very hard. So we introduced a new proof technique with proof unrolling. We call proof unrolling of cyclic proofs. So first, let me explain the proof sketch for the case of the symbolic heap separation logic. The SL0 is the symbolic heap separation logic, the core logic of symbolic heap separation logic. It contains only formulas representing shape of heap memories, and each variable represents an address of memory cells in heaps, and we have only 3 kinds of formulas and inductive predicates. This emp means that the heap is empty, and this we call x point to y. This x point to y, this formula means the heap consists of exactly 1 memory cell of address x, which stores the value y. And yes, this picture represents a heap satisfying this point to formula. Okay, so this A star B is the multiplicative conjunction. In the separation logic, we call this one separating conjunction, and it means the heap can be divided into 2 disjoint subheaps satisfying A and B. So these are the formulas of the symbolic heap separation logic, and we extend the formula by inductive predicates to represent some recursive data structure on heaps. Here is an example, very simple example of an inductive predicate LS. LS means the least segments. Yes, as this picture shows, this predicate represents some least segment from X to Y on heap. And here is another example, SLXY. It is similar to the predicate, this predicate LS, and in fact, it represents the same structure as this segment LS. but it defines the list segments in a different way. Okay, so for this symbolic heap separation logic, we can consider the cyclic proof system we call CSL0ID omega. Here are the inference rules of this cyclic proof system. One is axiom and cat and star rule, and these two unfolding rules for right-hand side and left-hand side. This left unfolding rule corresponds to the case analysis, depending on definitions of the inductive predicate P. It means to prove P enters B, we have to consider the cases of D1 to Dn if P is defined by D1 to Dn. Okay, for this cyclic proof system, we show that the cut-elimination does not hold. The counterexample is here, LS enters SL. As I stated, these predicates represent the same list segment, so this entailment is valid. And we can prove this entailment with cuts, but we cannot prove it without cuts. So I like to skip the detail of the cut-through proof. Here is the cut-through proof of this entailment LS enters SL. But the point is here, we use cut rule in this proof. And to prove the entailment is not provable without cut, we assume it's cut-free cyclic proof. Then we can see the proof must be of this form. In fact, on this rightmost pass here, we can use only unfolding rules. LU is the left unfolding rules and RU is right unfolding rules. Because yes, we can use only these unfolding rules because yes, we cannot apply star rule because the right hand side contains no star connective, and we cannot find any cycle on this rightmost pass because the sizes of the entailments strictly increase from bottom to top, so we can't find any cycle. Then we have to eventually apply the right unfolding rule here, but it must yield invalid entailment, and it contradicts with the soundness of the cyclic proof system. Yes, here's invalid entailment. In this way, we can find a contradictory path from any cyclic proof of LS enters SL. Yes, in the case of symbolic heap separation logic, we can find the contradiction on the right-hand side, rightmost path. Okay, for the symbolic heap separation logic, this proof goes well. Then can we extend this idea for the other logic? This counterexample for symbolic heap separation logic contains binary predicates. So what happens if we restrict the predicates to unary or nullary ones? For the first question, in SL0, symbolic heap separation logic, we can easily find a contradiction in the rightmost path of cyclic proofs. This is because SL0 is very restricted logic. In particular, it contains only multiplicative conjunctions, and the form of proof is very restricted. On the other hand, the bunch logic or the full separation logic, that logics have the ordinary conjunctions that admit the structure rules, weakening and contraction rules. Such structural rules makes the situation much harder because they yield much more possibilities of forms of the cyclic proofs. Okay, so to these questions, we give an answer. The cut-elimination fails in the cyclic proof system for the bunched logic either, and we can give a counterexample with only nullary predicates. From here, let me explain the main result of this work. The bunch logic is an extension of the sequent-calculus Elliot by the multiplicative conjunctions. Yes, it corresponds to the separating conjunction in separation logic. This logic was introduced for reasoning compositional properties of resources, and the separation logic is based on this bunched logic. So a bunched logic contains two kinds of conjunctions, the ordinary one and multiplicative one. So for the two kinds of conjunctions, the secants are also extended with so-called bunches. In bunches, we have two kinds of separators, comma and semicolon. These are corresponding to the multiplicative conjunction and ordinary conjunction. This comma corresponds to the multiplicative conjunction, and semicolon corresponds to the ordinary conjunction. So this bunch intuitively means this formula. So we consider this kind of sequence in bunched logic. Moreover, here we consider only nullary predicates. Okay, so the definition of formulas and bunches in bunched logic are here. We have two kinds of conjunctions, multiplicative one and the ordinary one, with units for multiplicative conjunction is I, and unit for the ordinary conjunction is top. Yes, this I corresponds to the emp in separation logic. And this P represents the inductive or atomic propositions, nullary predicates. And we have two kinds of separators, comma and semicolon, in bunches, and secants have this form, comma entails A. Yes, and the bunches are considered up to commutative monoid equations for comma and I and semicolon on top. So, for example, these three bunches, I, comma, gamma, and gamma, and the top semicolon gamma are identified. Okay, so for this bunch logic, we consider the cyclic proof system. Yes, in fact, this is a subsystem of Brotherstone's CLBI omega ID. Yes, this system contains the inference rules for star and conjunction, the ordinary conjunction. Yes, for each connective, we have two kinds of inference rules, left rules and right rules. And we have the same unfolding rules as the separation logic. And moreover, we have structure rules and cut. Yes, the main difference from the separation logic, symbolic heap separation logic, is the existence of structure rules. For semicolon, yes, this semicolon represents the ordinary conjunction, so we have structure rules for this semicolon. Okay, so this is the cyclic proof system for bunched logic, and the main result of this talk is this theorem: cut-elimination does not hold in CLBI omega ID. Okay, so here is the counterexample. It is very simple one, and it contains only nullary predicates, and it means the inductive propositions, P12 and P21. Similarly to the two least segment predicates, LS and SL, these P12 and P21 represent the same thing. So this sentiment is valid. Yes, these proportions, inductive proportions, represent this kind of formula: I star Q1 blah blah Q1 and Q2 blah blah Q2 for arbitrary number of Q1s and Q2s. But they are defined in different ways, and for P12 we have to expose Q1s first, and then we can get Q2s. And conversely, for P21, we have to expose Q2s first, and then we can get Q1s. So the outline of the proof is similar to the case of separation logic. We show this entailment. This entailment is provable with cut and not provable without cut. Okay, the difficult part is the impossibility of cut-free proof. As before, we assume a cut-free cyclic proof of P12 enters P21 like this. This is yes, this is an example of the cut-free cyclic proof of this entailment. In the case of separation logic, SL0, we can always find a contradiction on the rightmost path. But for this example, because of the structure rules here, C and W are structure rules, we have to consider more complicated possibilities or proofs. Yes, in fact, in this example, where is the contradiction? In fact, the leftmost path and rightmost path contain no contradiction. Yes, this cycle satisfies the soundness condition, and in fact, we can prove normally prove this entailment. So we have to chase the contradiction on this middle path. So how can we chase it for arbitrary cyclic proofs? To do this, we introduce the proof unrolling. And the proof unrolling itself is a very simple idea. It says from cyclic proof, we can construct a non-cyclic finite proof for any unfolded form of conclusion. For example, this part, I star Q1 blah blah Q1 is obtained by unfolding the predicate P12. That is a concrete instance of P12. Then from a cyclic proof, from any cyclic proof of P12 enters P21, we can construct a non-cyclic proof of this entailment by unrolling the cycles in this cyclic proof. For the previous example of cyclic proof, let's see how we can get the non-cyclic proof of I star Q1 star Q1. We construct the non-cyclic proof from bottom to top. First, we copy the contraction rule like this. Here in the left unfolding rule, this P12 is unfolded to P2 or P12 star Q1. And at this point, we choose a branch depending on the unfolding tree of P12 to obtain this I star Q1 star Q1. So we choose this branch. Then we copy L star and weakening rule like this, and left unfolding rule again. So here, this P12 is unfolded to P2 or P12 star Q1, and we choose the right branch because we obtain this I star Q1 from this P12. So then we copy this L star and weakening again, and the cycle is unrolled. And for this left unfolding rule, now we choose the left branch because yes, here this I is obtained from this P2. So continuing this process, we can get the non-cyclic proof of this conclusion. Yes, this is a non-cyclic proof. And the path in the non-cyclic proof corresponds to a middle path in the cyclic proof. And then we can show that for sufficiently large number of Q1s here, if we choose the unfolded form here for a sufficiently large number of Q1s, then the unrolled non-cyclic proof contains a path that corresponds to a contradictory path in the cyclic proof. So we can use the proof unrolling to detect a path in the cyclic proof, including contradiction. So we can prove the impossibility of cut-free cyclic proof of P12 enters P21. Okay, so let me conclude this talk. we prove the cut-elimination does not hold in the cyclic-proof system for the bunched logic, even if we restrict the inductive predicates to nullary ones, zero-ary ones. This proof by proof unloading can be adapted to the full separation logic and linear logic. As future work, we are interested in this cut-elimination of the cyclic proof system for the first order logic. Yes, and recently Masaoka proved the cut-elimination does not hold in cyclic proof system for the first order logic either. They use an elaborated idea to chase contradictory paths, and their counterexample contains ternary inductive predicates. So we'd like to adapt our proof idea to the first order logic, and we are interested in some restriction for arity of inductive predicates. Thank you for listening.
So let us thank the speaker. Thank you, Koji. I don't know how to produce a clap without unmuting all microphones, so it is better if I don't do it. I see there is a button for. Okay. So, any questions? You may send questions by chat, or you may just raise your hand. And I will check on the gallery if you are raising.
Anupam raised.
Anupam, I see. The first I see at least.
Yeah.
Alejandro, can you give the...
Yeah,
okay,
so
you may speak,
nice,
Anupam.
Thanks for the nice talk, Koji. So I had a question about approach. So I think one way of seeing this is to give you a lower bound on what you can do without cuts in the cyclic setting, which is a really interesting idea. But there's another approach, which is to say, well, if you can't prove something without cuts in the cyclic setting, how can we change the system so that you can? So maybe you're familiar with some of my works with Damien Proust on clean algebras and extensions. And we also had this result where we show that the cut-free cyclic system is not complete. It can't prove certain things that you can prove regularly with cut. But it turns out that if you add a little bit of structure into your sequence, and we have a form of hypersequent, you recover the completeness without cuts. So this could be another question. So in the case of bunched implications and related logics, do you think there might be a way of adding more structure to the system to actually recover some sort of cut-free cyclic completeness?
So sorry, what do you mean by the adding some structure?
To the sequence, to the lines of the proof.
Sorry?
To the lines of the proof. So like, so for example, going from sequence to hypersequence or something similar.
Okay.
So of course, bunched logics already have a lot of structure, but you can, there are works that can give even more structure.
Yeah. Honestly speaking, I have no idea about that such an extension. Yeah. Yeah. Sorry, I have no idea currently. Any possibility of the you mean the can we recover some recover the cut-elimination by extending some structure such a hyperstructure?
Well, cut-elimination.
Yeah. Sorry, I have no.
I think it would be. I think it would be interesting because you already have some works that do something like that.
Yeah.
So it would be interesting to see if you could measure how much you lose by at the level of the structure. Anyway, thank you.
Thank you.
More questions? I have a question which is in a sense the dual one of Anupam. So instead of adding more structure to proofs in order to recover cut-elimination, you could make the system weaker. So you could reduce the principle in your system in order to derive exactly what you may derive without cut. Is it possible, in your opinion? Did you consider it this alternative choice?
Sorry, I
may give you an example. I have the impression that if you use it in arithmetic, which is the only cyclic proof I know, that when you derive something without cut, then essentially is a constant time algorithm running in polynomial time, which means a very restricted kind of. So maybe if we could reduce strongly the principle in the logical or arithmetical system, we could just derive what we derive without cut. This would just be a way of knowing what we derive without cut, of course. Would that be a way of deriving more, as Anupam is suggesting?
Yeah, yeah. Yeah, actually, for that issues, I have no idea currently.
Okay, so but I think it would be worth to discuss this. More questions, messages? So if there are no more questions, it is right time for the next talk. So let us thank again the speaker. I don't know, I will clap in the old-fashioned style. I see people are clapping in a more technological style. Many thanks. So thank you again.